Welcome to our research section. In this video, I would like to show you how to find some precedents that are relevant for your resilient housing design and to extract the meaningful information from them so that you can utilize it in your own work. In our previous course, Resilient Architecture Research, we developed case studies that are about projects built in areas affected by natural hazards. We came up with 8 different proposals, and in the book which we are sharing with you, you have a summary of those proposals. These projects were based on areas that were affected by earthquakes, like for example Japan or Chile or Nepal. They were about areas affected by typhoons, like for example the Philippines, areas affected by floods like the Netherlands and also Mumbai. And in the book that I'm sharing with you, you can find all that information. We looked at different projects according to a number of criteria. First of all, speaking about the context and what natural disaster these countries are affected by, and then specific examples about the projects built in these areas. So here you see a project that is about the Ring of Fire, Pacific Ring of Fire, so basically all the areas that are suffering from earthquakes, starting from Chile, going to the east coast, the west coast of the United States, and then up to Alaska, and then down through Japan, China, Philippines, and down to Australia. So this is where most of the earthquakes are happening because that's where the tectonic plates are shifting. We looked at the case studies in Chile, for example, and explaining what exactly is going on, what are the most important earthquakes and the damage that they made. Then we studied some resilient typologies, buildings that are resilient to earthquakes and how they can withstand earthquakes. What are the structures, for example, here that are earthquake resilient? They have to be flexible. They don't have to be stiff, but flexible. They have to be able to move when the earth starts shaking. We also looked at some geometries. For example, here you can see what are the geometries that withstand earthquakes, like where the structure should be positioned, what's the proportion between the height and the width of a building in the ideal cases. Then afterwards, what we did is we divided the buildings research according to specific criteria. We looked at the building as if it were according to 2 principles. One is the idea of Le Corbusier, that the building is made just like the human body. It has the structure, which are the bones, then the spaces, which are the muscles, then the membrane, which are the skin, and then all the lymphatic and blood system, which are basically the installation inside the building. So that's his theory. The other theory, we looked at Gottfried Semper and his 5 points of architecture, which are the base, the structure, the membrane, the roof, and the fire inside the building. So we used these criteria as a way to approach the research. We started looking at structures, and here you see Resilient Structures chapter in the research, in vernacular architecture, and at the same time in contemporary buildings. So we looked at how traditionally this problem has been addressed and how in modern times it has been solved. Then we looked at enclosures. What is the building membrane, like how are the exterior walls built in a way that they can resist earthquake. For example, how they can be flexible enough so they don't get cracks when it starts moving and shaking. And what kind of membrane we can have for areas, for example, affected by storms or by floods. And remember, in many cases, natural disasters happen all together. So sometimes we have an earthquake, that causes tsunami, and then the tsunami causes flood, and then the flood causes some kind of nuclear disaster, as is the one that we have in Fukushima just 5 years ago. So this is about the enclosure. We then looked at the interiors or the mitigation strategies of a building. So for example, when there is a flood, what can be done so that the water kind of comes in and out of the building without damaging it? When there is an earthquake, what happens so that the spaces in the building can move and adapt to the kind of the movement of the building? Or if there's a typhoon, what can we do so that the building can withstand all the wind that comes from the side and heavy rain? We explored different case studies, like here, built with wood. In this case, it's Chile, houses that are built in part, so the architects would only build half of the part, half of the building, and then give it to the owners and allow them to expand in a few years when they needed more space, and also when they had enough money to expand and continue building the house. And last but not least, we looked at building systems. It's crucial to understand how a building can be self-sufficient. For example, when there's a typhoon or earthquake, many times the power system is affected. Here in New York, for example, we had Hurricane Sandy 5 years ago, and what it did is damage one of the power plants, so half the city was left without light. So we need to understand what are the buildings or what are the devices that we can use inside the building, like solar panels, batteries, that can provide temporary relief, or even in some rural cases where there is no access to the grid, can permanently provide electricity to the house. We also looked at recycling systems for the trash of the building, and also passive heating and cooling systems. So this is just one of the many examples that you would find in the research that the participants in our course did. I invite you to look and study all those solutions that you would find in this book, and to learn something from them that you can use in your own work.